Some important aspects of halogenation of alkanes. Relative reactivities of halogenation of alkanes. The order of reactivity of halogens in the various halogenation reactions of alkanes has been found to be fluorine, chlorine, bromine, iodine. In fact, in case of iodine, the reaction does not seem to take place at all. We would try to account for this observed order of reactivity by considering the energy changes during the chain initiating and propagating steps in the reaction of a particular alkanes with different halogens. Since energy of activation has not been measured for the various steps of all the reactions, the value of delta H for different steps derived from the bond dissociation energy would be of a lot of help to us. The value of delta H for each of the three most important steps during halogenation of methane with different halogenation are as follows. The first step merely involves the dissociation of halogen molecules, and therefore delta H can be taken to be equal to E activation. Thus, iodine having the least E activation should dissociate more rapidly, followed by fluorine, bromine, and chlorine in this order. But this order of dissociation goes against the observed order of reactivity of halogen. This means that the first steps cannot be responsible for the observed order of reactivity. The third step, involving the reaction of methyl radicals with halogen, is found to be exothermic in all the four cases, and the value of delta H is nearly the same for chlorine, bromine, and iodine. For all these reactions, E activate is expressed to quite small, and the actual value is possible not more than a fraction of a kilojoule in any case. Thus, this step also cannot explain the observed reactivities as it appears to take place with equal ease in all the cases. Coming to the second step, which involves the extraction of hydrogen of methane by halogen atom, we observe a wide variations in the values of delta H. The value of E activation for this step are found to be 17 kJ to 75 kJ respectively for reactions involving chlorine and bromine atoms. In case of highly exothermic reaction with fluorine atoms, the E activation is expected to be very low, about 1 to 2 kJ, while for the highly endothermic reaction with iodine at atom E activation must naturally be at least 138 kJ. This implies that the fraction of effective collision in this step should be in the order fluorine, chlorine, bromine, iodine. It is this fraction of effective collision which controls the overall reaction. For instance, the actual fraction of effective collisions between chlorine atom and methane is found to be 1 in 40 at 548 Kelvin, while it is in 1 in 10 million in case of bromine atoms and methane at the same temperature. Due to the very small fraction of its effective collision with methane, it is quite likely that a bromine atom may happen to collide against another bromine atom or a methyl radical during its search for the property oriented methane molecule for an effective collision with it. This means that a chain reaction involving a particular bromine atom may get terminated before long. It is found in actual practice that average chain length involving bromine is less than 100, while in case of chlorine it runs into several thousands. It is therefore evident the rate of chlorination of methane and other alkanes should be much faster than bromination, in spite of the fact that the chlorine molecules dissociate into atoms more slowly than bromine molecules. In case of fluorination, fluorine atoms are not only formed faster than the chlorine or bromine atoms due to lower E activation of step 1, but also length of reaction chain are much longer due to E activation of step 2 being only about 1 to 2 kJ. At the same time, the overall fluorination reaction is highly exothermic, delta H being for minus 427, minus 104.5 and minus 34.5 respectively. In case of overall process of fluorination, chlorination and bromination, all these factors taken together justify the explosive nature of fluorination of alkanes. For iodinations to be carried out, E activation for second step must be at least 138 kJ. Even with this value, the fraction of effective collision between methane and iodine atom work out to be 1 in 10 to the power 12 at 548 Kelvin. Evidently, this is too low a fraction to allow any reaction propagating chain to function. This is why iodinations take place only at a negligible rate, even though iodine atoms are formed from their molecules at a comparatively faster rate. It may be noted that the most vital step in halogenation, step 2, involves the formation of halogen acids. Now, the bond dissociation energy of HF, HCl, HBr, and HI are 569, 430, 468, and 297 kJ more inverse. The order of hydrogen halogen bond strength, it may be seen, is the same as the order of reactivity of halogen. In halogenation of alkanes, this indicates that the reactivity of halogens towards alkane is linked to the strength of hydrogen halogen bond. The more the strength of hydrogen halogen bond, the more the reactivity of halogens in the halogenation of alkanes. Further, the strength of hydrogen bond determines the stability of halogen acids. Therefore, it may also be stated that more the stability of halogen acid forming during halogenation, more is the reactivity of halogenation. To conclude this discussion, it may be emphasized that the most important and rate determining step in the halogenation of alkanes is the chain propagating step 2. It is also be to noted that the overall halogenation of alkane except iodination proceeds at quite a fast rate, even though the E activation for the chain initiating step is quite high. This is because the decomposition of even one molecule of halogens led to the formation of many molecules of alkyl halides due to the repetition of step 2 and 3 time and again. Thus, the overall reaction works out to be quite fast in spite of the initially slow dissociation of halogenation. Transition state for halogenation. It has been already stated that the vital step in the halogenation alkane RH plus X negative gives R radical plus HX. The energy of activations for these steps, which controls the overall process, is obviously equal to the difference in energy between the reactants and the transition state. Let us have a close look at this transition state, the formation of which is so important for the progress of halogenation. In this transition state, the carbon-hydrogen bond of the alkane is somewhat stretched but not completely broken, while a new hydrogen bond of the alkane is somewhat stretched. While a new halogen bond has been partially formed. At the same time, the odd electron, which is on halogen in case of reactants and on alkyl groups in case of products, is divided between the two in the transition state. For depicting such a state, dotted line may be used for indicating partially broken and partially formed bond, while the symbol delta may be employed for representing each atom's share of the odd electrons as shown below. The transition state leading to the formation of a particular free radical has some of the properties of that free radical. Thus, the free radical and the corresponding transition state have the same order of stability and ease of formation. Relative reactivities of alkane in halogenation and relative reactivity of different class of hydrogen atoms. If a mixture of equimolar amount of two or more alkane is allowed to react with a limited quantity of fluorine and bromine, the product obtained consists of a mixture of different alkyl halides corresponding to the alkanes taken, but the relative quantities of alkyl halide in the mixture are not the same. This means that different alkenes exhibit different degrees of reactivities while reacting with a particular halogen. These relative reactivities of alkanes can be attributed to the reactivities of different classes of hydrogen atoms present in them. It has been found that irrespective of the al- it has been found that irrespective of the alkanes in which they are present, the relative activities of hydrogen follows the order tertiary, secondary, primary. The hydrogens of methane being lesser reactive than even primary hydrogens. To have an idea of the magnitude of difference in the reactivities of different hydrogen atoms, let us consider the reaction between a mixture of equimolar amount of ethane and methane and a small quantity of fluorine at 298 Kelvin in the presence of light. It is found that the amount of ethyl chloride is formed is about 400 times as much as that of methyl chloride. This means that ethane is 400 times as reactive as methane. Allowing for that fact, the ethane contains 6 hydrogen atoms while methane has only 4. Each primary hydrogen of ethane is still about 267 times as reactive as each hydrogen of methane. The relative reactivities of different classes of hydrogen atoms may be explained by considering the relative stabilities of alkyl radicals formed in the steps which controls the overall process of halogenation. For instance, in case of fluorination of methyl and ethane, the respective rate controlling step may be written as methane plus chlorine radicals gives methyl radical plus HCl. Ethane plus chlorine radicals gives ethyl radical plus HCl. Relative to the respective parent alkanes, ethyl radical, a primary radical, is more stable than the methyl radical. As such, the transition state leading to the formation of this radical must be more stable than the transition state generating methyl radical. Consequently, the transition state of ethyl radical must have lesser E activation than the transition state of methyl radical. Therefore, the transition state in the former case must be formed more readily than the latter. In other words, the carbon hydrogen bond in ethane gets stressed and ultimately breaks more readily than the carbon hydrogen bond in methane. That is why primary hydrogen atom in ethane are said to be more reactive than the hydrogen atom in methane. Similarly, the still greater reactivities of secondary and tertiary hydrogen atoms can be explained in terms of the greater stabilities of secondary and tertiary alkyl radicals. Thus, it may be concluded that reactivities of different classes of hydrogen atoms, which determines the relative rates of halogenation of different alkanes, follow the same order as that of relative stabilities of corresponding alkyl radicals, that is, tertiary, then secondary, then primary, and then methane.